Welcome to Computing Fundamentals 2. This video about an introduction to trees. So in this video we are going to define the trees, rooted trees, and the properties of trees. And also we will discuss some of the application of trees. A connected graph that contains no simple circuit is called a tree, and trees were used as long ago as 1857. They have used them to count certain types of chemical compounds. Since that time, trees have been employed to solve problems in a wide variety of disciplines, as the examples in this video will show. Trees are particularly useful in computer science, where they are employed in a wide range of algorithms. For instance, trees are used to construct efficient algorithms for locating items in a list. They can be used in algorithms such as Huffman coding that construct efficient codes, saving cost in data transmissions and storage. Trees can be used to study games such as checkers and chess. Trees can be used to model procedures carried out using a sequence of decisions. Constructing these models can help determining the computational complexity of algorithms based on a sequence of decisions such as sorting algorithms. Procedures for building trees containing every vertex of a graph, including depth-first search and breadth-first search, can be used to systematically explore the vertices of a graph. Exploring the vertices of a graph via depth-first search, also known as backtracking, allows for systematic search for solutions to a wide variety of problems, such as determining how 8 queens can be placed on a chessboard so that no queen can attack another. We can assign weights to the edges of a tree to model many problems. For example, using weighted trees, we can develop algorithms to construct a network containing the least expensive set of telephone lines linking different network nodes. We have showed how graphs can be used to model and solve many problems. In this video, we will focus on a particular type of a graph called a tree, so named because such a graph resembles trees. For example, family trees are graphs that represent the chart of the family. Family trees use vertices to represent the members of the family and edges to represent parent-child relationships. The family tree of the male member of the Bernoulli family of Swiss mathematicians is shown in Figure 1. The undirected graph representing a family tree restricted to people of just one gender and with no inbreeding is an example of a tree. To understand these concepts further, let us formally define trees. A tree is a connected and directed graph with no simple circuits. Because a tree cannot have a simple circuit, also the tree cannot contain multiple edges or loops. Therefore, any tree must be a simple graph, as we can see from the following example. Which of the graphs shown in Figure 2 are trees? G1 and G2 are trees, because both are connected graphs with no simple circuits. G3 is not a tree because E, B, A, D, E is a simple circuit in this graph. Finally, G4 is not a tree because it is not connected. Any connected graph that contains no simple circuits is a tree. What about graphs containing no simple circuits that are not necessarily connected? These graphs are called forests and have the property that each of their connected components is a tree. Figure 3 displays a forest. Trees are often defined as undirected graphs with the property that there is a unique simple path between every pair of vertices. Theorem 1 shows that this alternative definition is equivalent to our definition. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. Now we will try to prove this theorem. First, assume that T is a tree. When T is connected graph with no simple circuits, let X and Y be two vertices of T. Because T is connected by theorem 1 of graph connectivity, there is a simple path between X and Y. Moreover, this path must be unique. For if there were a second such path, the path formed by combining the first path from X to Y followed by the path from Y to X obtained by reversing the order of the second path from X to Y would form a circuit. This implies using that there is a simple circuit in T. Now, as a hint, there is a unique simple path between any two vertices of a tree. Now assume that there is a unique simple path between any two vertices of a graph T. Then T is connected because there is a path between any two of its vertices. Furthermore, T can have no simple circuits. To see that this is true, suppose T had a simple circuit that contained the vertices X and Y. Then there would be two simple paths between X and Y because the simple circuit is made up of a simple path from X to Y and a second simple path from Y to X. As a hint, a graph with a unique simple path between any two vertices is a tree. Now, let us discuss another type of trees. It's called rooted trees. In many applications of trees, a particular vertex of a tree is designated as the root. Once we specify a root, we can assign a direction to each edge as follows. Because there is a unique path from the root to each vertex of the graph by theorem 1, we direct each edge away from the root. Thus, a tree together with its root produces a directed graph called a rooted tree. A rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. Now we will try to prove this definition by an example. Rooted trees can also be defined recursively. We can change a rooted tree into a rooted tree by choosing any vertex as the root. Note that different choices of the root produce different rooted trees. For instance, figure 4 displays the rooted trees formed by designating A to be the root and C to be the root. Respectively, in the trees T, we usually draw a rooted tree with its root at the top of the graph. The arrows indicating the directions of the edge in a rooted tree can be omitted because the choice of root determines the direction of the edge. The terminology for trees has a potential to express the definition. Suppose that T is a rooted tree if V is a vertex in T other than the root. The parent of V is the unique vertex U such that there is a directed edge from U to V. The viewer should show that such a vertex is unique. When U is the parent of V, V is called a child of U. Vertices with the same parent are called siblings. The ancestors of a vertex other than the root are the vertices in the path from the root to this vertex. The ancestors of a vertex other than the root are the vertices in the path from the root to this vertex, excluding the vertex itself and including the root. That is, its parent, its parent's parents, and so on, until the root is reached. The descendants of a vertex V are those vertices that have V as an ancestor. A vertex of a rooted tree is called a leaf. If it has no children, vertices that have children are called internal vertices. The root is an internal vertices unless it is the only vertex in the graph, in which case it is a leaf. If A is a vertex in a tree, the subtree with A as its root is the subgraph of the tree consisting of and its descendants and all edges incident to these descendants. In the rooted tree, which root A, shown in figure 5, find the parents of C, the children of G, the siblings of H, and all ancestors of E. The solution for example 2. The parent of C is B. The children of G are H, I, and J. The siblings of H are I and J. The ancestors of E are C, B, and A. The descendants of B are C, D, and E. The internal vertices are A, B, C, G, H, and J. The leaves are D, E, F, I, K, L, and M. The subtree rooted at G is shown in figure 6. Rooted trees with the property that all of their internal vertices have the same number of children are used in many different applications. Later in this video, we will use such trees to study problems involving searching, sorting, and coding. A rooted tree is called an M-array tree if every internal vertex has no more than m children. The tree is called a full M-array tree if every internal vertex has exactly m children, and an M-array tree with m equal 2 is called a binary tree. To understand this definition, we will take an example. Are the rooted trees in figure 7 full M-array trees for some positive integer m? T1 is a full binary tree because each of its internal vertices has 2 children. T2 is a full array tree because each of its internal vertices has 3 children. In T3, each internal vertex has 5 children, so T3 is a full 5-array tree. T4 is not a full M-array tree for any m because some of its internal vertices have 2 children and others have 3 children. An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. Ordered rooted trees are drawn so that the children of each internal vertex are shown in order from left to right. Note that a representation of a rooted tree in the conventional way determines an ordering of 4 its edges. We will use such orderings of edges in a drawing without explicitly mentioning that we are considering a rooted tree to be ordered. We will use such orderings of edges in drawings without explicitly mentioning that we are considering a rooted tree to be ordered. In an ordered binary tree, usually called just a binary tree, if an internal vertex has 2 children, the first child is called the left child and the second child is called the right child. The tree rooted at the left child of a vertex is called the left subtree of this vertex, and the tree rooted at the right child of a vertex is called the right subtree of the vertex. The reader should note that for some applications, every vertex of a binary tree, other than the root, is designated as a right or left child of its parent. This is done even when some vertices have only one child. We will make such designations whenever it is necessary, but not otherwise. Ordered rooted tree can be defined recursively. Binary trees, a type of ordered rooted tree, as we are going to see in the following slides. Let us take an example about ordered rooted trees. What are the left and right children of D in the binary tree T shown in figure 8a, where the order is that implied by the drawings? What are the left and right subtrees of C? The left child of D is F, and the right child is G. We show that the left and right subtrees of C in figures 8b and 8c respectively. Just as in the case of graphs, there is no standard terminology used to describe trees, rooted trees, ordered rooted trees, and binary trees. Trees are used as models in such diverse area representing organization. The structure of a large organization can be modeled using a rooted tree. Each vertex in this tree represents a position in the organization. An edge from one vertex to another indicates that the person represented by the initial vertex is the direct boss of the person represented by the terminal vertex. The graph shown in figure 10 displayed such a tree. In the organization represented by this tree, the Director of Hardware Development works directly for the Vice President of R&D. We will often need results relating to the number of edges and vertices of various types in trees, as we can see from the following definition. A tree with n vertices has n-1 edges. The number of vertices in a full M-array tree with a specified number of internal vertices is determined, as Theorem 3 shows. As in Theorem 2, we will use n to denote the number of vertices in a tree. A full M-array tree with I internal vertices contains n equal n multiplied by I plus 1 vertices. So in this video, we managed to define trees, rooted trees, and we will discuss some properties of trees. Also, we have explained some of the application of using trees in some disciplines like computer science and management. Thank you for watching this video and see you in the next one.